All right, welcome back. So this is an ALEKS topic that's called solving a basic calorimetry problem, and I think this is a great topic. I think it's got a lot of complicated aspects, but once you get a handle on it, it's actually very straightforward. It's actually not that hard. But if you don't have that fundamental understanding, right, the conceptual knowledge, then it's going to be very difficult. So let's go ahead and get into it. The first thing you'll notice, I've put a few notes here. Let's not get distracted by that just yet. We're going to talk about what the problem says, what's going on, and then we'll get into what I've written here. So we have this sample of iron. So this is my block of iron, and I'm going to drop it into this calorimeter. It's got 200 grams of water, and the iron starts off at 90.5 degrees. This is a fairly common setup for a problem like this. We're going to take a hot rock or a hot piece of metal or something. We're going to drop it into some water. We're going to get some energy transfer. And that energy transfer is really the whole point of this chapter. The whole point of thermodynamics is to understand these energy transfers. So the temperature of the water starts off at 15 degrees. When the temperature of the water stops changing, it's 17.8 degrees. So we could calculate how much energy has gone into raising the temperature of the water. The pressure remains constant at 1 atmosphere. That's just telling us that no work is done. In chemistry, oftentimes we just ignore work. Everything's really done at constant pressure for chemists on the benchtop. But that's more physics. So if you're more interested in physics, go do that. Okay. Calculate the specific heat capacity of iron according to this experiment. So it obviously doesn't want you to just look it up. We're going to be looking for, sort of what the question of this question is S equals question mark, right? So what is that specific heat? When we're using the equation Q equals S times M times delta T. Okay, so once we have this sort of idea, we're going to drop the hot rock in. There's going to be an energy transfer. Then what we need to start thinking about is from the different points of view. So there's two different points of view that we really need to consider. The point of view of iron, so this is our sample. The iron's going to be losing energy. So we could say that the Q value, Q is going to be a measure of the energy, is negative. We're losing energy. Where does that energy go? The water absorbs it. So the water gains the energy, so the Q value should be positive. And then this is really the key here. The quantity of energy, the Q value, that should be the same. But the sign is going to be different depending on the point of view. So I think students get really confused with this and the whole sign thing. This really breaks it down the proper way for us to sort of consider it and to think about it. But I'll talk about some like shortcuts or ways that we can sort of get around it. So now the next question then becomes, well, what can I solve for? Is there a quantity that I can solve for? So we're looking for some information for the iron. So I think pretty clearly that's not going to be our starting point, right? We're going to figure out, well, from the point of view of the water, what can we do? So if we think about this equation, Q equals S times M times delta T, I'm choosing to use this equation because we're given, the mass of the water, we're given a delta T, a temperature change. For water, we know that the specific heat is 4.184. So we sort of have all the information that we need to calculate the amount of energy that the water would be gaining as it goes from 15 degrees Celsius to 17.8 degrees Celsius. So that would look like this. Q equals 4.184. Keep in mind the units here, joules over grams times degrees Celsius, times the mass of the water is 200 grams, times our delta T. So it's going to be T final minus T initial. So keep in mind that this delta T is T final minus T initial. So then that's going to give us a delta T of 2.8 degrees Celsius. We can do this calculation. You should see that your grams and your degrees Celsius will cancel out. And then we'll be left with an answer of positive 2,343.04. Probably not that important to have all that, but joules of energy. So this is the amount of energy that the water absorbs, and we know that basically just from doing the simple calculation. If you want to know how much energy that water absorbs as it changes temperature, we need to know the specific heat capacity, which we know is given. We need to know the mass, which again we know is given, and we need to calculate the delta T. T final minus T initial, so this 17.8 is T final, 15 degrees is my T initial, so I get a positive 2,300 joules of energy that the water absorbs. Now we're going to sort of move over and we're going to say, well, from the point of view of the iron, the Q value Q equals S times M times delta T. Again, we're looking for this S value. That's the goal of the problem. The Q value from the water, we're going to move over here, but we're going to change the sign. We're going to say minus 2,343.04 joules equals S for my iron times my mass of iron, which is 58.8, times my delta T. And again, delta T is T final minus T initial. So my change in temperature, if this is my initial 90.5 and this is my final 17.8, 17.8 T final of the water and the iron is going to be the same T final, right? They're in this solution together, minus 90.5 degrees Celsius. Gives me a delta T of minus 72.7 degrees Celsius. So this is where that sort of sign convention comes into play, right? Because my temperature is going down, that's really telling us that we're going to be losing energy, that our Q value should be negative. So this, sign convention should match up, right? And going from this positive Q value to a negative Q value, that's because we're changing the point of view. The quantity of energy is the same, but the sign is different based on the point of view. So let's go ahead and calculate this S value here. If you do that calculation, you should get S equals 0.548. The units here would be joules. We've got units of joules, grams, and degrees Celsius over grams times degrees Celsius. So that's our units here for our final answer. So that's looking good. And then we want to round to 2 sig figs. So 2 sig figs would be 0.55 joules over grams times degrees Celsius. So that is our answer for this problem. And just sort of going back through, making sure we understand, all aspects of this. The take-home message here is that our quantity of energy should be the same. The sign's going to be different. Now, if you're getting to this point here, you can really, just sort of use your common sense and sort of say, well, I know that the delta T is 72.7. I know that's an absolute value delta T. And I know that, when I do this calculation, my specific heat capacity should be a positive value. Maybe you forget one of these signs, these negative signs. You see that S value, you see that maybe in your calculation it's negative. Just use your common sense, right? You can sort of get away with some of this. I think that's probably some of the danger as well. You can get away with some of this of just by saying, well, what do I know it should be? I know the mass should be positive, right? We're not going to have a negative mass. I know the specific heat capacity should be positive. Doesn't make sense that it would be negative. So, you could sort of get away with that a little bit, but having this understanding and really being able to follow this through is going to be really valuable, I think, as you move forward. So that's the process for this type of problem. All the different versions are just basically same idea, but solving for different things. Hope that helps.